In the unforgiving vacuum of space, chemistry dictates a cold, inevitable march toward equilibrium. Elements bind, react, and settle into stable, quiet states over the span of billions of years. A dead world is a mathematically balanced world. Its atmosphere is a closed, predictable ledger where every chemical equation zeroes out perfectly, leaving nothing but inert rock and silent gas. Imagine a sprawling, deserted metropolis at 3 in the morning. Everything is static. The electrical grid is powered down, and there is no residual heat of hidden activity. That is the baseline state of the cosmos, absolute stillness. But when a planetary atmosphere outright refuses to balance, when it clutches onto a volatile, fragile gas that should be obliterated by ultraviolet stellar radiation almost as soon as it is born, the mathematics of that world violently shift. It means something down in the dark is actively manufacturing that gas faster than the local star can burn it away. Something relentless, an engine continuously fighting against the decay of entropy. To detect this kind of microscopic war against planetary decay, we built a $9 billion eye of gold and beryllium, parking it 1,000,000 miles from Earth in the freezing, absolute dark of Lagrange Point 2. We aimed its mirrors at a faint red dwarf star located 120 light-years away in the constellation of Leo. The target was an exoplanet heavily cloaked in mysteria, massive world trapped in a twilight orbit. The objective was seemingly routine. Watch the planet pass in front of its host star, wait for the starlight to filter through its alien atmosphere, and read the absorbed wavelengths like a barcode across a cosmic scanner. We were looking for the mundane, the standard inventory of a heavy, ocean-bearing world: carbon dioxide, methane, perhaps the thick vapor of an endless sea. Instead, hidden deep within the infrared telemetry, buried beneath the static noise of interstellar dust, the instruments returned a phantom signature, a spectral peak so specific, so incredibly out of place, that it fractured our fundamental assumptions of planetary chemistry. On our own planet, this exact molecular configuration is not born from the heat of volcanoes. It is not forged in the crushing pressure of tectonic plates or the electrical violence of atmospheric storms. It is an exclusive byproduct of biological machinery, microscopic life, breathing and dying in the oceans. And we have just detected its undeniable shadow drifting in the winds of a world we can never hope to reach. The raw data sits on the servers, quietly mocking the boundaries of our isolation. If you seek truth in the dark, if you demand to understand the cold mechanics of the void without the comforting veil of human delusion, subscribe and join us. We are descending into the architecture of an anomaly that might just redefine our place in the dark. But before we can comprehend the terrifying weight of this single molecule, we must first dismantle a deeply entrenched error in our own intuition. We have spent decades searching the sky for a perfect mirror image of Earth, assuming that the physics of survival require a pale blue dot, and in doing so, we have fundamentally misunderstood the true, violent nature of water. For centuries, our gaze upward has been polluted by a crippling, comforting narcissism. When we stare into the galactic void, we are not truly looking for alien worlds. We are desperately searching for a mirror. We want to see ourselves reflected in the dark. We imagine distant planets as pale blue dots draped in wispy white clouds, orbiting gentle, warm, yellow suns. This anthropic, biased, the arrogant assumption that the universe wants to build Earths has deeply infected our intuition. We assume that the physics of survival are inextricably linked to the specific, quiet conditions of our own local neighborhood. But the cosmos is not a factory designed to produce temperate Edens. It is a terrifyingly violent, chaotic engine. And to understand the gravity of what is happening on K2-18b, we must first mercilessly deconstruct everything you think you know about planetary habitability. The first illusion we must shatter is the romanticized concept of the habitable zone. In popular culture, it is often called the Goldilocks zone, a term that reduces the brutal mechanics of astrophysics to a child's fairy tale. The idea is simple, perhaps too simple. A region around a star where the temperature is just right for liquid water to exist on a planet's surface. Not too hot, lest the oceans boil away into space. Not too cold, lest the world freeze into a dead, icy tomb. It is a calculation governed by a cold, elegant piece of mathematics known as the planetary equilibrium temperature, expressed as $T underscore equals T underscore SQRT, frac R underscore 1 a dollar. It calculates the balance between the incoming stellar radiation and the planet's albedo, or reflectivity. But this equation, while mathematically pure, is inherently blind to the chaotic reality of stellar behavior. Our Sun is a jet-type main-sequence star. It is remarkably stable, predictably burning its hydrogen fuel with the quiet hum of a well-maintained generator. But G-type stars are the anomaly. They make up less than 8% of all stars in the Milky Way. The true lords of the galaxy are the M-dwarfs, the red dwarfs. They account for nearly 3/4 of the stellar population. They are small, dim, and ancient, burning so slowly that their lifespans are measured in trillions of years. K2-18b orbits one of these crimson ghosts. To the untrained mind, a small, dim star sounds peaceful. It is not. Red dwarfs are notoriously volatile. Because they are less massive, their interiors are entirely convective. The boiling plasma from their nuclear cores churns violently all the way to the surface, generating magnetic fields of incomprehensible power. These stars do not warm their planets gently. They lash them with devastating ultraviolet flares and X-ray storms. Imagine standing in a pitch-black room, trying to warm your hands, not by a campfire, but by the unpredictable, sputtering bursts of an industrial blowtorch. That is the reality of the red dwarf habitable zone. Furthermore, to maintain enough heat for liquid water, a planet must orbit incredibly close to a red dwarf, often closer than Mercury is to our Sun. At this suffocating proximity, the orbital mechanics become hostile. The gravitational gradient across the planet's diameter acts like a vice, forcing the world into tidal locking. The planet's rotation slows until it perfectly matches its orbit, freezing one hemisphere in eternal, scorching daylight, while the other is plunged into an endless, frozen night. The only theoretical refuge on such a world is the Terminator line, the twilight strip between the inferno and the abyss. This is the environment of K2-18b, a massive world bathed in infrared crimson, perpetually locked in a gravitational stare-down with a violent star. And yet, when we aimed our telescopes there, we were initially thrilled to find water. This brings us to the second great illusion of our intuition, the false prophecy of water. We are taught from a young age that water is synonymous with life. Follow the water has been the rallying cry of astrobiology for decades. We celebrate every time a probe finds frost on a Martian crater or geysers erupting from the icy crust of Enceladus. Because we are born of water, we project biological intent onto a purely thermodynamic process. But when you look at the universe through the cold, objective lens of chemistry, the presence of $H_20 is not a miracle. It is a cosmic inevitability. Consider the raw ingredients of reality. Hydrogen is the lightest, simplest, and most abundant element in existence. It is the primordial ash of the Big Bang, making up roughly 75% of all baryonic mass in the universe. Oxygen, on the other hand, is forged in the crushing pressures of dying stars and blasted into the interstellar medium through supernova explosions. It is the third most abundant element in the cosmos. When you mix the first and third most common elements in the universe over billions of years, they will inevitably find each other. They will bind. Water is not a delicate, rare elixir. It is, quite literally, the rust of the universe. It is the most basic thermodynamic cooling fluid available to the cosmos. Finding water on an exoplanet does not mean you have found a biosphere. It simply means you have found a place where the laws of chemistry are functioning exactly as expected. But how do we actually know what a planet 120 light-years away is made of? We cannot send a probe. We cannot scoop the atmosphere into a vial. The distance is a physical barrier that renders our fastest spacecraft effectively motionless. To bridge this terrifying gap, we rely on the ghosts of light and the architecture of quantum mechanics. In 1814, a German glassmaker named Joseph von Fraunhofer aimed a telescope through a prism at the sun and noticed something unsettling. The beautiful, continuous rainbow of the solar spectrum was scarred. It was sliced by hundreds of stark, black lines. Fraunhofer did not know what they were, but he meticulously mapped them. He had unwittingly discovered the barcodes of reality. Decades later, quantum physicists realized that these dark gaps were the shadows of atoms. When a photon of light travels from a star, it carries a specific amount of energy, dictated by its wavelength. If that photon passes through a cloud of gas, the atmosphere of an alien planet must navigate a minefield of molecules. Every molecule, whether it is carbon dioxide, methane, or water, has a unique quantum structure. The chemical bonds holding the atoms together vibrate, stretch, and bend at highly specific frequencies. If a passing photon's energy perfectly matches the resonance frequency of a molecular bond, the photon is absorbed. It is consumed, entirely erased from existence, translated into the internal kinetic energy of the molecule. When the James Webb Space Telescope observes K2-18b, it is not taking a photograph. It is waiting for the planet to eclipse its host star. For a few fleeting hours, the red dwarf's light filters through the thin halo of the planet's atmosphere before continuing its 120-year journey to our mirrors. Webb captures this light and spreads it out using its near-infrared spectrograph, or UNIR-SPEC. It looks for the missing light. It looks for the microscopic black lines where photons were slaughtered by alien molecules. The depth and width of these absorption lines give us a perfect, indisputable ledger of what is floating in the skies of that distant world. And this is where K2-18b begins to shatter our fundamental models. This planet is not a scaled-up version of Earth. It has a mass nearly 9 times greater than our home, and a radius 2.6 times larger. In the rigid taxonomy of astrophysics, it is classified as a subneptune, or more specifically, a candidate for a Hycean world. The word itself is a portmanteau of hydrogen and ocean. Human intuition fails completely when trying to visualize this environment. Do not picture the Pacific Ocean under a cloudy sky. Picture an abyssal, global ocean of water, potentially boiling under the immense, crushing pressure of a titanic atmosphere made almost entirely of hydrogen and helium. Hydrogen is not a passive gas. In planetary chemistry, an atmosphere dominated by hydrogen is known as a strongly reducing environment. It is a chemical regime that aggressively drives reactions toward the lowest possible energy state. In a reducing atmosphere, thermodynamics acts like a heavy blanket, smothering chemical complexity. Oxygen atoms are violently forced into binding with hydrogen to form water. Carbon atoms are pressured into binding with hydrogen to form methane. Nitrogen is forced into ammonia. Imagine a massive, frictionless clockwork mechanism. A reducing atmosphere is a clock that has fully unwound. Every chemical reaction that can happen has happened. The molecules have settled into their most stable, unreactive configurations. If any complex, volatile molecule were to spontaneously form in this environment, it would be a fleeting aberration. The immense pressure of the hydrogen envelope, combined with the searing ultraviolet bombardment from the red dwarf star, would act as a cosmic incinerator. Volatile compounds would be ripped apart, their constituent atoms quickly reassimilated into the stable, dead equilibrium of methane and water. This is the baseline reality of K2-18b. It is a world of extreme gravity, shrouded in a primordial gas, baked by a chaotic star. It should be a chemical vault, a closed thermodynamic system where nothing interesting ever happens, because the math dictates that nothing interesting can happen. But when the data from the honor-spec instrument was finally decoded, the scientists did not just see the expected boring shadows of water and methane sitting quietly in the spectrum. Precisely at a wavelength of 3.4 microns was a spike, a faint but undeniable absorption signature that had no right to be there. It was the spectral fingerprint of a molecule so fragile, so chemically volatile, that its very existence in a hydrogen-rich atmosphere is a paradox, according to every model of planetary physics. This molecule should be destroyed by the stellar wind almost instantaneously. Its presence cannot be explained by the slow, dead grinding of geology. It cannot be explained by photochemistry. It defies the heavy, unwound clockwork of the reducing atmosphere. For this molecule to exist in the observable quantities Webb detected, it must be continuously, aggressively replenished. Something on that dark, crushing world is actively fighting the laws of thermodynamics. We have stripped away the illusion of the Earth-like mirror. We have established the violent, sterile mechanics of the red dwarf and the Hycean ocean. The stage is set. The parameters of the impossible are locked in place. The math tells us K2-18b is dead. But the light, the 120-year-old light, caught in our beryllium mirrors, tells us something else entirely. It whispers of a process we have only ever seen in one other place in the entire observable universe. To truly grasp the magnitude of the anomaly found on K2-18b, we must first confront the terrifying scale of the space that separates us from it, and the agonizing precision required to bridge that abyss. 120 light-years is not merely a distance, it is a temporal and physical gulf that breaks the human capacity for visualization. It is roughly 1.1 quadrillion kilometers. If you were to board a vessel traveling at the speed of the Voyager 1 probe, the fastest object ever built by human hands, tearing through the vacuum at over 60,000 kilometers per hour, your journey to this red dwarf would take more than 2 million years. We are profoundly, inescapably isolated. We cannot touch this world. We cannot send machines to taste its waters or sample its atmospheric strata. The only physical connection we will ever have with K2-18b is a microscopic rain of ancient photons, particles of light that were born in the nuclear furnace of a volatile red star, filtered through an alien sky and hurled across the interstellar void. The light captured by the James Webb Space Telescope to make this discovery did not leave K2-18b yesterday. It departed in the early years of the 20th century, right around the time humanity was first learning to construct powered flying machines. For over a century, these photons traveled in absolute silence, navigating the sparse, freezing dust of the interstellar medium, untouched and undisturbed. They carried within them a cryptographic message written in the language of quantum mechanics, a fragile imprint of the molecules they encountered. To intercept this message before it was lost forever in the vastness of the Milky Way, we had to construct an observatory of unprecedented, almost psychotic precision. The Webb telescope is not just a mirror, it is a masterpiece of cryogenic engineering, forced to operate at temperatures that mimic the death of the universe. To see the faint infrared signatures of distant worlds, the telescope itself must emit no heat. It sits behind a 5-layer sunshield of Kapton, a tennis court-sized umbrella that passively cools the optical payload to under 50 Kelvin. But for the most sensitive instruments, 50 degrees above absolute zero is still a roaring inferno. The mid-infrared instrument is actively refrigerated by a closed-loop cryocooler down to an agonizing 7 Kelvin. Only in this absolute, shivering dark can the beryllium mirrors, plated with a layer of gold, merely hundreds of atoms thick, catch the incredibly faint infrared echoes of an exoplanet transit. When K2-18b passes in front of its host star, the event is not spectacular. It is not an eclipse that plunges the system into darkness. The planet is a tiny silhouette against a massive stellar disk. The total amount of light reaching Webb drops by a fraction of a percent. But we are not interested in the solid, opaque body of the planet that blocks the light completely. We are interested in the translucent halo, the infinitesimally thin sliver of atmosphere clinging to the planet's gravitational well. During the transit, a minuscule fraction of the star's light grazes the edge of the planet, passing through this atmospheric ring before continuing to Earth. This is where the scale of the measurement becomes truly horrifying. The starlight that passes through the atmosphere represents perhaps tens of parts per million of the total light received. We are looking for a shadow within a shadow, a fractional dimming caused by molecules absorbing specific wavelengths of light. To extract this data, the photons are fed into the near-infrared. Here, a micro-shutter Araya grid of nearly 250,000 microscopic doors, each the width of a human hairpin's, and closes to isolate the target star, blocking out the background noise of the cosmos. The light is then slammed into a grating that fractures it into an incredibly detailed spectrum. Astrophysicists analyzing this spectrum look for the transmission depth at various wavelengths. They are searching for the absorption cross-section of specific molecules, defined mathematically by the equation $O lambda in 10 sigma lambda na zeta. This elegant formula calculates the optical depth $O as a function of wavelength, determined by the absorption cross-section of the molecule $sigma and its number density and integrated along the path the light takes through the altitude $z. In a hydrogen-dominated atmosphere like K2-18b, the scale, height, the vertical distance over which the pressure drops by a factor of $E is unusually large. Hydrogen is incredibly light, allowing the atmosphere to puff out, expanding the physical size of the translucent halo. It is this specific architectural feature of a Hycean world that allowed Webb to peer deep into its molecular inventory. When the data pipeline finally cleared, the spectrograph delivered the expected signatures. The deep, heavy gouges in the spectrum caused by methane and carbon dioxide were unmistakably present, confirming the existence of a massive, carbon-rich envelope, and the distinct lack of ammonia strongly supported the theoretical model of a global, liquid water ocean lying beneath the crushing atmosphere. The baseline was established. The world was behaving according to the grim, heavy rules of a reducing environment. But as the data was meticulously scrubbed for artifacts, an anomaly emerged from the noise floor, a subtle, spectral absorption feature located precisely at 3.4 microns. It was a faint signal, hovering dangerously close to the limits of statistical significance. Yet it persisted across multiple data reduction pipelines. It was not a ghost in the machine. It was a physical reality in the sky of K2-18b, and it was the spectral fingerprint of $C_2H_6S dimethyl sulfide. To understand the sheer absurdity of this molecule existing in this specific environment, we must dissect its architecture. Dimethyl sulfide, or DMs, is an organosulfur compound. It consists of a single, central atom of sulfur, chemically bound to two methyl groups clusters made of one carbon atom and three hydrogen atoms. On our pale blue dot, DMs is responsible for the distinct, briny odor of the ocean. It is the smell of the sea, but stripped of its earthly, poetic associations. DMs is a highly volatile, fragile, and energetically demanding molecule. The bonds between the carbon and sulfur atoms vibrate and stretch, creating the exact resonance frequencies that absorb light at 3.4 microns, the very wavelength Webb detected. The existence of dimethyl sulfide in a hydrogen-dominated atmosphere under the glare of a red dwarf is a chemical paradox of colossal proportions. To grasp the scale of this mystery, imagine a grand, ancient library built entirely of dry parchment and old wood. Now imagine discovering a lit candle sitting perfectly still in the center of the room. The candle itself is not impossible, but its continued existence in an environment so profoundly primed to extinguish it or be consumed by it implies that someone or something is actively maintaining the flame. K2-18b is an environment fundamentally hostile to a molecule like DM. The atmosphere is saturated with hydrogen gas, aggressively reducing any complex molecules into simpler, lower energy states. Furthermore, the red dwarf star, K2-18, is a violent neighbor. Although it is cooler and dimmer than our sun, it is highly active in the ultraviolet spectrum. The relentless bombardment of high-energy UV photons hitting the upper atmosphere of the exoplanet creates a brutal photochemical regime. These photons carry enough kinetic energy to completely shatter the fragile carbon-sulfur bonds of dimethyl sulfide through a process called photolysis. The molecule is ripped apart almost as soon as it is exposed to the starlight. The half-life of DMs in the upper atmosphere of a world like this is incredibly short. It is a chemical ghost, destined to be erased by the stellar wind. Yet, the absorption line in the Webb data tells us it is there. And it is there in quantities large enough to cast a shadow that can be seen across 120 light-years of empty space. This is the crux of the terror. This is the scale of the impossibility. For dimethyl sulfide to maintain a stable, detectable presence in an atmosphere that is actively attempting to obliterate it. There must be a source, and not just a minor, passive source. There must be an engine of staggering scale, churning deep within the crushing darkness of the planet, manufacturing hundreds of thousands of tons of this specific organosulfur compound and pumping it into the sky at a rate that mathematically outpaces the destructive power of a star. We must look down. We must descend from the thin, irradiated upper atmosphere where the photons were absorbed, and plunge into the abyss of the Hycean Ocean. The scale of this ocean mocks the Pacific or the Atlantic. It is a planetary scale volume of water, likely hundreds of kilometers deep. The pressure at the bottom of such an ocean is so immense that water no longer behaves as a familiar liquid. It is compressed into exotic phases of solid ice, such as Ice 7, a crystalline structure forged not by cold, but by the sheer, crushing weight of gravity and hydrodynamics. Above this ice mantle lies the liquid ocean, dark, unfathomably deep, and perpetually churning. The interface between this gargantuan ocean and the thick hydrogen atmosphere is a zone of extreme chemical tension. The pressure is crushing, the temperature is trapped by an intense greenhouse effect, and the gases are dissolved into the liquid under conditions that we can only replicate in heavily armored, laboratory pressure vessels. If dimethyl sulfide is being produced, it must be originating here in the liquid layer and then surviving a treacherous vertical journey. It must well up from the black depths, breach the supercritical interface of the ocean surface, and diffuse upward through hundreds of kilometers of thick, dense hydrogen gas, fighting against the atmospheric currents, until it finally reaches the stratosphere where Webb can see it. The logistics of this molecular migration are staggering. The sheer volume of DMs required to saturate the atmosphere enough to leave a spectral imprint is astronomical. We are forced to ask, what mechanism is capable of such relentless high-volume production of a complex, volatile organosulfur compound? Astrophysicists and planetary geologists have exhausted themselves attempting to model a non-biological origin. They feed the parameters into supercomputers, the planetary mass, the irradiation, the presumed atmospheric metallicity, the thermodynamics of sulfur. They run the simulations, desperately trying to find a dead geological pathway to manufacture $C_2H_6S. They model intense volcanic activity, imagining titanic, submerged calderas, erupting sulfur dioxide into the crushing deep. They model complex, high-temperature, hydrothermal vent systems reacting with the carbon-rich ocean. They attempt to force the unwound clockwork of the reducing atmosphere to rewind itself through sheer geological violence, but the models fail. Inorganic chemistry is stubborn, without the guiding hand of biological enzymes to lower the activation energy. The creation of dimethyl sulfide from raw sulfur and carbon under these specific conditions is energetically unfavorable. The math refuses to cooperate. Volcanism can produce sulfur dioxide. It can produce hydrogen sulfide, but it does not spontaneously assemble the specific, complex symmetry of dimethyl sulfide in the vast quantities required to fight off the photolytic destruction of a red dwarf. The scientific community stands at a precipice, staring down into the data with a mixture of awe and profound unease. The detection of DMs on K2-18b is not a quiet discovery. It is an alarm bell ringing in the deepest vacuum of space. It is a glaring neon sign blinking in a dead, gray desert. We have found a thermodynamic anomaly of planetary proportions. we have found an engine that should not exist. Every time we have encountered a mystery of this scale in the cosmos, from the perfectly regular pulses of the first discovered quasars to the eerie, dark gaps in protoplanetary disks, the answer has always been a new, terrifying mechanism of dead physics, a spinning neutron star, a nascent gas giant sweeping up dust. We have been trained by history to expect the mundane, to trust that the universe is lifeless, cold, and strictly obedient to the mindless laws of entropy. But as the supercomputers continue to fail, as the dead, geological models crash against the inflexible wall of chemistry, the shadow of a different kind of architecture begins to loom over K2-18b. We are being forced to consider a mechanism that is not dead, a mechanism that actively consumes energy, processes matter, and excretes chemical anomalies as a fundamental byproduct of its existence. We are approaching a threshold that, once crossed, will irreversibly fracture our understanding of the dark. The scale of the mystery is no longer just about the size of the ocean or the violence of the star. It is about the terrifying resilience of the anomaly itself, fighting an unwinnable war in the upper atmosphere of a distant, alien abyss. The data forces us to ask, not just what is making the gas, but how such a complex, delicate mechanism could possibly survive in the crushing, dark hell of a Hycean world. To understand the violent collision between our current models of reality and the data beamed back from Lagrange Point 2, we must look away from the stars for a moment and look downward into the microscopic, brutal machinery of our own oceans. We must dissect exactly how dimethyl sulfide is forged on Earth, because it is not a passive byproduct of geology. It is the exhaust fume of a relentless, unseen war for survival. On our planet, $C_2H_6S is produced almost entirely by phytoplankton, specifically microscopic marine algae such as Amelia huxley. But these organisms do not manufacture this complex molecule for the benefit of the atmosphere. They synthesize its chemical precursor, dimethyl sulfonatiopre, or DMSP, out of sheer, desperate necessity. Imagine living in an environment that is actively trying to crush and dehydrate your cells simultaneously. That is the reality of a saline ocean. The high concentration of salt in seawater creates severe osmotic pressure. If a microscopic cell does not actively balance its internal chemistry with the external environment, the water inside its cellular membrane will be violently drawn out into the ocean, and the cell will instantly collapse. To prevent this thermodynamic execution, phytoplankton act as microscopic factories, binding sulfur and carbon into DMSP. This molecule acts as an osmolyte, a heavy internal ballast that stabilizes the cell against the crushing, dehydrating weight of the sea. The organism expends a massive amount of its biological energy. It's ATP driving this endergonic chemical reaction against the natural gradient of entropy. But DMSP is not what the James Webb Space Telescope detected. DMSP remains trapped inside the living cell. The transformation occurs only in death. When these microscopic algae are infected by marine viruses, or when they are ruthlessly grazed upon by zooplankton, their cellular membranes are ruptured. The internal ballast spills out into the open water. Here, in the chaotic aftermath of this microscopic slaughter, specific bacterial enzymes known as DMSP lyases encounter the spilled molecules. They act as chemical cleavers, aggressively snapping the chemical bonds of the DMSP molecule. It is a highly specific, catalyzed degradation. The molecule is split, and one of the primary fragments discarded in this enzymatic butchery is dimethyl sulfide. This volatile gas, highly insoluble in seawater, immediately begins to outgas. It bubbles upward from the photic zone, breaks the surface tension of the ocean, and bleeds into the atmosphere. This is the only way this molecule exists on our pale blue dot. It is the chemical ghost of a biological massacre. It requires a vast, interconnected ecosystem of producers and consumers, a microscopic economy of life and death, just to maintain a trace presence in our air. Now, project this violently biological mechanism across 120 light-years of hard vacuum. Apply this earthly architecture to the lightless, crushing depths of K2-18b. If the signature in the atmospheric data is real, it suggests a terrifyingly familiar scenario playing out in an utterly alien environment. The Hycean ocean of K2-18b, trapped under the staggering weight of a hydrogen-helium atmosphere, would possess an internal pressure and chemistry so extreme that any theoretical biology would face an osmotic and thermodynamic nightmare far worse than our earthly seas. It is logically consistent that if life exists in that dark, boiling abyss, it would need a powerful, complex osmolyte to prevent its own structural annihilation. And it is entirely possible that, in the event of its death, a similar enzymatic cleavage occurs, releasing DMs to float up through the heavy, reducing atmosphere. But this is where we slam into the brutal, unforgiving barrier of astrophysics. The tantalizing logic of biology is paralyzed by the cold, mathematical reality of statistical confidence. The universe does not offer us the luxury of definitive answers. It only provides probabilities buried beneath a mountain of static. When astrophysicists isolate the absorption spike at 3.4 microns, they are not looking at a perfectly clean, unambiguous photograph of a molecule. They are staring at a jagged, noisy line graph. The data collected by the near-infrared spectrograph is inherently contaminated by the chaotic thermal noise of the telescope's own instruments. The cosmic ray hits on the detector array, and the unpredictable, slight variations in the red dwarf's stellar output during the transit. To separate a genuine chemical signature from this chaotic background, astronomers rely on the concept of the signal-to-noise ratio, expressed mathematically as $SNR equals frac mu underscore sigma underscore dollar. In observational astronomy, a detection is measured in standard deviations, or sigma dollar, mapping to the probability density function of a normal distribution, Fx equals frac sigma skirt E frac left frac dollar. This mathematical framework dictates our certainty. A 1 sigma detection means there is a roughly 32% chance that the signal is nothing more than a random fluctuation of background noise, a phantom born of statistical bad luck. A 2 sigma detection brings that probability of error down to about 5%. It is intriguing, it is enough to write papers and secure funding, but it is not proof. In the strict, unyielding court of particle physics and astrophysics, the gold standard for claiming a definitive discovery is 5 sigma confidence level of 99.99994%. At 5 sigma, the chance of the signal being a random fluke is about 1 in 3.5 million. The detection of dimethyl sulfide on K2-18b currently hovers maddeningly between 1 and 2 sigma. It is a whisper, barely audible over the roaring static of the cosmos. This low statistical confidence fractures the scientific community, creating a bitter, agonizing theoretical impasse. We are standing before a locked, heavily armored door. The keyhole is shaped exactly like a biological process, but the room is too dark to see if the lock has actually turned. The skeptics, armed with the necessary rigor of the scientific method, rightly point out the immense danger of false positives. They argue that the resolving power of the telescope, while unprecedented, still has limits. The resolving power is defined as $R equals frac dollar, where $LAMBD, a dollar, is the wavelength, and $delta, LAMBD, a dollar, is the smallest difference in wavelength that can be distinguished. At 3.4 microns, the absorption line of dimethyl sulfide sits perilously close to the spectral absorption lines of other, far more mundane molecules, particularly methane. Methane is abundant on K2-18b. It is expected. It is thermodynamically cheap. And at low resolutions, or when heavily broadened by the immense pressure and temperature of the alien atmosphere phenomenon known as pressure broadening, where collisions between gas molecules perturb their quantum energy states, the deep, wide spectral gouge of methane can bleed over and create a deceptive shoulder in the data. It can mimic the faint, narrow spike of DM. The telescope might not be seeing a biological exhaust fume. It might simply be misinterpreting the blurred, heavy shadow of a dead, reducing gas. This creates an epistemological nightmare. We are trapped in a scenario where the most profound discovery in human history might just be an artifact of overlapping quantum shadows. To resolve this overlap, to narrow the error bars and push the detection from a mere suggestion to a 5 sigma certainty, requires more transits. It requires pointing the James Webb Space Telescope back at that specific red dwarf, staring perfectly still, and accumulating more photons. But JWST is the most contested piece of scientific hardware in existence. Every hour of its observational time is fiercely fought over by thousands of astrophysicists desperate to study early galaxies, dying stars, and black holes. Securing the necessary hundreds of hours to confirm a faint, controversial spike on a single exoplanet is a bureaucratic and logistical war of attrition. And even if we secure the time, even if we stare at K2-18b until the error bars shrink to nothing, and the 3.4 micron spike stands out with absolute, undeniable 5 sigma clarity, we are confronted by a second, far more terrifying barrier, the barrier of our own ignorance. Let us assume the signal is perfectly real. Dimethyl sulfide is undeniably swirling in the upper atmosphere of that heavy world. Can we instantly declare the existence of an alien biosphere? No. We are immediately ambushed by the concept of unknown unknowns in inorganic chemistry. We only know what dimethyl sulfide means on Earth. Our entire chemical intuition is forged in the specific temperature, pressure, and elemental abundance of our own crust and oceans. What if the universe has a cold, dead mechanism for manufacturing $C_2H_6S that we simply lack the imagination to comprehend? Consider the environment of K2-18b. It is a regime of extreme physics. The bottom of the Hycean Ocean operates under pressures and temperatures that shatter our laboratory models. Water at those depths exists as supercritical fluid or exotic, high-pressure ice phases. What if, at the boundary where the silicate core meets this supercritical ocean, the extreme geophysical violence acts as a bizarre, non-biological catalyst? What if there is some unknown, highly complex hydrothermal pathway, driven by the intense magnetic induction of the red dwarf and the crushing planetary gravity, that forcefully bonds carbon and sulfur without the need for cellular machinery. We have no proof that such an abiotic pathway exists. Current thermodynamic models suggest it is virtually impossible for geological processes to synthesize DMs in these quantities while fighting the rapid photolytic destruction in the upper atmosphere. The math screams that it must be biology, but the haunting reality of astrobiology is that the universe is not obligated to conform to our chemical models. It has billions of years and billions of worlds to run blind, chaotic experiments. The cosmos is an infinitely patient engineer. It might have found a purely mechanical, dead way to assemble this fragile molecule, rendering the biological explanation nothing more than a reflection of our own desperate desire to not be alone. This is the agonizing paradox of K2-18b. We have built an instrument capable of seeing the microscopic chemistry of a world a million times further away than our own sun. We have successfully caught the light. We have decoded the shadows. We have found a chemical signature that defies everything we know about the dead mechanics of a reducing atmosphere. The evidence points a trembling finger toward a staggering conclusion: a massive submerged alien biosphere fighting a desperate war against the thermodynamics of a hostile star. But the final step, the translation of that chemical ghost into an established, immutable truth, is blocked by a wall of statistical noise and the paralyzing fear of our own scientific blind spots. We are forced to look at an undeniable anomaly, knowing that the engine producing it is either the greatest biological discovery in the history of our species, or a terrifyingly complex manifestation of dead physics that we are entirely unequipped to understand. And as the telescope moves on to its next target, leaving the data to be debated and dissected in sterile rooms back on Earth, the anomaly remains, drifting in the dark, unresolved, waiting in the howling atmospheric currents of a world we can never touch, powered by an unseen mechanism that refuses to stop churning. Let us step across the threshold. Let us assume, for a moment, that the statistical noise settles, that the overlapping quantum shadows are meticulously cleared away, and the 3.4 micron spike is proven undeniable. Let us confront the reality that the engine churning in the dark, high-pressure abyss of K2-18b is, in fact, biological. If this is true, the discovery does not simply add a new footnote to a planetary science textbook. It fundamentally and violently rewrites the architecture of our existence. It means everything we have told ourselves about the miracle of life is a comforting delusion. We have spent centuries looking at our pale blue dot, viewing our biosphere as a fragile, highly improbable lottery ticket. We thought that the exact distance from the sun, the exact chemical composition of our atmosphere, and the exact, quiet sequence of geological accidents were the mandatory prerequisites for life to emerge. But if biology can take root and thrive in a strongly reducing, hydrogen-choked atmosphere under the crushing weight of a global ocean, while being mercilessly lashed by the ultraviolet flares of a volatile red dwarf, then life is not a delicate, rare phenomenon. It is an aggressive, inevitable thermodynamic symptom of the cosmos. To understand this, we must strip life of its poetry and reduce it to its mathematical skeleton. In 1944, the physicist Erwin Schrödinger proposed that life is essentially a mechanism that feeds on negative entropy. The second law of thermodynamics is absolute. The total entropy of an isolated system can never decrease over time. The universe is constantly moving toward maximum disorder, a state of cold, dead equilibrium. But a living organism is a localized pocket of intense, aggressive order. It maintains its highly structured internal chemistry by relentlessly extracting energy from its environment and excreting heat and degraded matter back out. It is mathematically defined by the condition $Ds underscore equals frac $0 within its localized boundary, constantly fighting the macroscopic decay of the universe. If the dimethyl sulfide on K2-18b is the exhaust of this process, it proves that this localized rebellion against entropy is not a fluke of our earthly oceans. It is a universal principle of physics. Given a sufficient energy gradient, even one as brutal as a supercritical ocean interface irradiated by an M-dwarf matter will spontaneously organize itself into complex, self-sustaining engines. This realization delivers the final, most devastating blow to our cosmic ego. It is the ultimate, terrifying extension of the Copernican principle. In the 16th century, we were violently displaced from the geographic center of the solar system. In the 19th century, Darwin displaced us from the biological center of creation, proving we were merely another branch on a blind, chaotic evolutionary tree. Now, the telemetry from Lagrange point 2 threatens to displace us from our chemical and existential center. We are not the universe's favored children. If life is a thermodynamic inevitability in conditions that extreme, then the Milky Way is not a sterile desert dotted with a single, fragile oasis. It is a teeming, infected petri dish, trillions of worlds trapped in the twilight terminators of red dwarfs might harbor crushing, blind, pressure-cooked biospheres. We are surrounded by an unfathomable volume of biology, but this sudden crowding of the universe introduces a new, suffocating paradox. If the cosmos is infected with life, why is it so agonizingly silent? The answer does not lie in the realm of sociology or the failure of alien engineering. It lies in the cold, unyielding tyranny of Einstein's relativity. The true barrier between us and the rest of the universe is not silence, it is latency. The speed of light, denoted as $c$, is approximately 299,792 kilometers per second. It is the absolute speed limit of causality. It is the maximum rate at which any information, any consequence, or any mathematical truth can propagate through the fabric of space-time. This constant is not merely a velocity measurement, it is a cage. In the mathematics of general relativity, the boundary of what we can possibly know or interact with is defined by our past light cone. Everything outside of this cone is physically inaccessible. It does not exist in our reality yet. When we observe the spectral data of K2-18b, we are not seeing the planet as it is. We are seeing it as it was 120 years ago. The photons that struck the beryllium mirrors of the James Webb Telescope began their journey at the dawn of the 20th century in the framework of Minkowski space-time. There is no such thing as a universal now. Two events separated by vast distances cannot be said to occur simultaneously in any absolute sense. We are fundamentally, physically, severed from the present reality of the exoplanet. If that abyssal ocean harbors an evolutionary pathway that eventually leads to a complex, technological consciousness, we are blind to it. If they build massive machines beneath the ice, if they poison their own heavy atmosphere, or if their red dwarf unleashes a superflare that sterilizes the planet in a single, silent flash of exorius, we will not know for over a century. The speed of light ensures that we are permanently trapped in the past of everything we observe. We are ghosts looking at other ghosts. We often romanticize the concept of first contact as a synchronized conversation across the stars, a sudden sharing of cosmic knowledge. But the physics of the universe strictly forbid this. A dialogue across 120 light-years requires 240 years just to say hello and receive an answer. Generations of human scientists would live and die waiting for a single data point to return. The sheer scale of the abyss renders communication practically impossible. We are functionally alone in a crowded room. We might be surrounded by biological engines, some primitive, some incomprehensibly advanced, but the geometry of space-time ensures that we can never touch them, never trade with them, never truly know them. They are locked behind a wall of time, existing purely as mathematical anomalies in a stream of ancient light. And it is within this temporal isolation that the most crushing consequence of K2-18b reveals itself. It is a matter of stellar lifespans and the ultimate fate of our respective biospheres. Human intuition is tightly bound to the rhythms of our G-type star. The sun has been burning for 4.5 billion years, and it will sustain this stable main sequence phase for roughly 5 billion more. It feels like an eternity, but our biosphere does not have that long. In a little over 1 billion years, the sun's core will begin to contract and heat up, increasing its luminosity by a mere 10%. That slight shift in mathematical output will be enough to trigger a runaway greenhouse effect on Earth. Our oceans will evaporate into the atmosphere. The water molecules will be shattered by solar radiation, and the hydrogen will bleed away into space. The carbon silicate cycle will halt. The delicate, fragile mechanism of earthly life will be entirely incinerated, leaving a dead, baking rock wrapped in a suffocating shroud of carbon dioxide. Our time here is a brief, transient spark. The red dwarf, K2-18, operates on a fundamentally different, infinitely more terrifying timescale. Because M-dwarfs are so small and have fully convective interiors, they do not build up an inert core of helium that eventually chokes the nuclear reaction. They continuously churn their hydrogen fuel from the surface to the core, burning it at a painstakingly slow, miserly rate. A star like K2-18 will not live for 10 billion years. It will burn for trillions of years. It will vastly outlast our sun. It will outlast the main sequence of almost every other bright star we can currently see in the night sky. Long after our sun has expanded into a red giant, swallowed the inner planets, incinerated the Earth, and collapsed into a cold, dense white dwarf, K2-18 will still be there. It will still be casting its dim, infrared glow onto the thick, heavy atmosphere of K2-18b. If a biosphere has truly managed to anchor itself in the crushing, violent environment of that Hycean ocean, it has secured a front-row seat to the end of the universe. It does not need to invent faster-than-light travel. It does not need to frantically colonize the stars to survive the death of its local sun. The biological engine churning out dimethyl sulfide is fueled by a stellar furnace that will outlive human history, human evolution, and the Earth itself by orders of magnitude that utterly defy our comprehension. We look at K2-18b through our telescopes, and we imagine an alien hell. We see a pressurized tomb trapped under a hostile alien sky. But the cold, brutal mathematics of astrophysics tell a completely inverted story. We are the anomaly. We are the fragile, ephemeral ghosts haunting a dying, fast-burning solar system. The heavy, dark, reducing worlds orbiting the slow-burning red dwarfs are not the freaks of the cosmos. They are the standard, They are the permanent residents. When the last of the yellow suns burn out, and the galaxy slowly goes dark over the next 100 billion years, the twilight terminators of the M-dwarfs will be the only places left holding back the tide of entropy. And as we stare into the data pipelines, desperately trying to parse the microscopic shadow of a single molecule, we are forced to realize that whatever is down there in the crushing dark, breathing and dying in a boiling, heavy ocean, it does not need us, it will never know us, and long after our civilization is dust, it will still be there, relentlessly churning in the deep. We stand at the very edge of our understanding, holding a string of numbers and a faint, jagged line on a graph. The James Webb Space Telescope has already pivoted its beryllium mirrors away from the constellation of Leo. It is currently staring into the dust of distant nebulas and the dying light of ancient galaxies. The observation window for K2-18b has closed. The data we have is the only data we will get for the foreseeable future, trapped in a paralyzing limbo between statistical noise and paradigm-shattering truth. And as we debate the transmission depths and the photochemical half-life of a single organosulfur molecule, the universe simply continues its heavy, mindless churning. We want the universe to be a story, an ascending narrative where human consciousness is the ultimate, triumphant protagonist. But the crushing gravity of K2-18b and the violent glare of its red dwarf tell a different story. They tell a story of cold mechanics and thermodynamic inevitabilities. If the dimethyl sulfide detected in that alien atmosphere is simply an artifact of bizarre, high-pressure, inorganic chemistry, it is a stark reminder of our own ignorance. It means the cosmos possesses dead engines of such staggering complexity that they can perfectly mimic the breath of life, mocking our earthly intuition. It means we do not even know the rules of the game we are trying to play. But if the shadow at 3.4 microns is real, if it is the genuine exhaust of a microscopic war raging in the black, boiling depths of a Hycean ocean, the implications are far heavier. It strips away the final layer of our cosmic exceptionalism. It means that life is not a fragile, precious flame that needs to be sheltered. It is a relentless, aggressive infection. It is an emergent property of matter that will forcefully claw its way into existence even under the most hostile, irradiated, crushing conditions imaginable. It means the void is not empty. It is crowded, and it is entirely indifferent to us. The red dwarf, K2-18, will continue to burn for trillions of years. Whatever biological or mechanical process is venting that gas into the alien sky will outlast the Earth. It will outlast the sun. It will outlast every monument, every memory, and every line of code our species has ever produced. When our solar system is nothing but a cold, dead nebula, the twilight terminator of that heavy world will still be there, locked in its perpetual stare-down with its violent star. We are a fleeting spark in a fast-burning system, looking out into a universe dominated by ancient, slow-burning giants and dark, heavy oceans. We have finally looked deep into the abyss, and for the first time, we have found something that might be breathing back, but it is not speaking to us. It is not waiting for us. It is simply existing in the dark, fighting its own war against entropy, separated from us by an insurmountable wall of time and space. We are left with nothing but the numbers, the silence of the vacuum, and the terrifying realization of our own absolute insignificance.